Good afternoon, class. We are looking at Chapter 4, Application of Derivatives, 4.4, Optimization Problems. We covered 4.1, maximum and minimum values, 4.2, how derivatives affect the shape of a graph, and now 4.4, optimization problems. As you can see, we have a lot of differentiation formulas. Delta y, which is f of x plus delta x minus f of x, versus dy, which is f prime of x dx. Delta y is change along the curve, dy is the change along the tangent line. If you draw a tangent line using the point slope, we call it L of x. So L of x, or linearization, refers to finding the tangent line, everybody. Recall maximum or minimum points on a curve, local or relative extreme values. Local minimum occurs at the point C in an open interval of A to B in the domain if f of C is less than or equal to f of x for all x values in the open interval, in some interval. Local maximum occurs at the point C in an open interval A to B in the domain if f of C is larger than or equal to f of x for all x values in the open interval. Meaning, in short, peaks and valleys. This is the local mean, this is the local max, this is the local mean, this is the local max. Absolute, also known as global extreme values for, or extrema, are either maximum or minimum points on a curve. Absolute minimum occurs at the point C if f of C is less than or equal to f of x for all x values in the domain, the entire domain. Absolute minimum occurs at the point C if f of C is larger than or equal to f of x for all x values in the domain. So as you look at these two examples, local mean, local max, local mean, local max, local mean, local max. This local minimum for this shape is also an absolute minimum. This local max for this shape is also an absolute max. Critical point, we define it as follows. A critical number or point of a function f is a number c such that f prime is either 0 or does not exist. The methodology, you find f prime, you say it equal to 0 or it does not exist or it's undefined. Extreme value theorem, also known as a closed interval theorem, applies to a continuous function in a closed interval of A to B. The methodology number 1, find CP's critical points. How do we find them? F prime is 0 or doesn't exist. 2, find the functional value at A and B as well as the endpoints. And then absolute max is the largest value. Absolute mean is the smallest value. How derivatives affect the shape of a graph theorem. A function f is increasing where f prime is positive. A function is decreasing where f prime is negative. So as you look at this one, assuming it's a line, has a positive slope. This one, assuming it's a line, has a negative slope. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a function. In short, it means that we are looking at the peaks and valleys, everybody, at the as far as the interval of a graph. A function is concave up where f double prime is positive, meaning f prime is increasing, and a function is concave down where f double prime is negative or f prime is decreasing. So this is concave up. This is concave down. An inflection point C is a point where concavity changes. Inflection points occur where f double prime is 0 or does not exist, and the shape looks like that. Now, 4.4 optimization problems. Optimization problem is the problem of finding the best solution from all feasible solutions. In other words, find a solution in the feasible region which has the minimum or maximum value of the objective function. Examples: maximizing profit, minimizing cost, maximizing area enclosed. The first derivative test for absolute extreme values. Suppose that C is a critical number of a continuous function f defined on an interval. If f prime is positive for all x less than c and f prime is negative for all x larger than c, then f of c is the absolute maximum value of f. If f prime is less than 0 for all x less than c, and f prime is larger than 0 for all x larger than c, then f of c is the absolute minimum value of f. In other words, when you do the first derivative test using the sign graph, it should work for the entire domain for it to be absolute. And to do so, in short, the first derivative test for absolute extrema, a local extremum, is an absolute one if it's the one and only extremum. So if you have one extremum, then it becomes an absolute. So second derivative test says the same thing. Second derivative test for absolute extrema on an interval. If there is exactly how many? One critical number. Let f be continuous on an open interval of a to b, with only one critical number in the interval. If f prime is 0 and f double prime is positive, then f of c is the absolute minimum of f on the open interval of a to b. If f prime is 0 and f double prime is negative, then f of c is the absolute maximum of f on the open interval of a to b. In short, both of them refer to the following fact that if you happen to have one critical point, everybody, and an open interval, local becomes absolute. Whether you go with the first or the second derivative test makes no difference. Example one, a farmer has 2,400 feet of fencing and wants to fence up a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? One way is to just make up a rectangular shape with various dimensions, and area is the width times the length, and you sort of guesstimate the area. That's not a proper way of doing it. So what is the proper way of doing it? Define your variables. Let x represent the width, let y represent the length, and A is the area. So we want the largest area. So the objective is to maximize the area, which is x times y. Twenty-four hundred feet of fencing refers to constraint, limiting factors. So it is subject to the constraint such that we have 2,400 feet of fencing. Normally, the perimeter for the rectangular shape is 2x plus 2y. We don't need anything on this side. In this case, it's 2x plus y equals 2,400 feet of fencing. A is a function of two variables, x and y, and the methodology is to make it a function of one variable. And to do so, you solve for y becomes 2400 minus x. And put that into a. Now a becomes a function of one variable, namely x only, so it becomes x times 2400 minus 2x. And if you distribute, you get 2400x minus 2x squared. Now, x must be between 0 and 1200. Why is that? First and foremost, x is a dimension, must be positive. Secondly, if you look at this one and set this equal to 0, x becomes 1200, which means when x is 1200, this becomes 0, the area becomes 0, can't be 1200. But what if it's larger than 1200? This becomes negative, area becomes negative, can't be. Therefore, x must be between 0 and 1200, everybody. To find critical points, we find a prime 400 minus 4x. We set it equal to 0, x becomes 600. So what do we have? We have an open interval with one critical point. So whether we do the first or second derivative test makes no difference. The result tells us that local becomes absolute. So the first derivative test, and I'm going to do both, you need a number line from negative to positive infinity normally, but here we need 0 to 1200 and x is 600. At x equals 600, a prime is 0. To the left of 600, you can even pick 0 for test, but pick 1, for example, becomes what? Positive. To the right, let's say 700 becomes negative. Positive means increasing, arrow up. Negative means decreasing, arrow down. So 600 is a location of a local max. However, because it's an open interval with one critical point, it becomes an absolute max. The second derivative test is even easier. We get -4. And the methodology is that you have to evaluate it at the CP, in this case, x equals 600, because this is independent of x. You can't do anything. It's just always -4. Negative means concave down, looking like this, means maximum. So maximum occurs when x is 600. You put it back into the constraint to find the missing y, becomes 1200. And the largest area is the product of these two numbers, which results in 720,000 square feet. Example 2, find two numbers whose sum is 80 and whose product is a maximum. We should always define the variables. Let them be x and y or any variable of your choice. What is the objective? The product must be maximized. So maximize P equals X times Y. What is the constraint? Subject to the constraint, the sum X plus Y must be 8. P, you always go to the objective function and make it a function of one variable. P has two variables, X and Y. So you solve for Y from the constraint and you replace the Y with AD minus X and you distribute for the next part, and X must be Z between 0 and 80. Y is that. We want to maximize the product. If X is 0, the product is 0. What if it's larger than 80? If you set this one equal to 0, everybody, X becomes 80. So if you choose larger than 80, the parenthesis 80 minus X becomes negative. Negative times positive is negative. Because you're maximizing, you don't want 0, you don't want negative product. If you were minimizing, would be a different story. That's why X is between 0 and 80. And now P prime, we use this one, 80 minus 2X. We set this equal to 0 in order to find the critical point, which becomes X equals 40. We go with the second derivative test. P double prime is just negative 2. You have to evaluate it at the critical point, but it is independent of that. There is not much you have to do. So P double prime is negative. That's what matters, the sign. Negative means concave down, looking like that, and therefore it's maximum at X equals 40. So if it's maximum at X equals 40, you put it back into the constraint to find the missing Y. That becomes also 40. And the maximum product is the product of 40 and 40, or 1600. That's pretty straightforward. A farmer with 240 feet of fencing wants to build an E-shaped enclosure besides a creek as seen in the diagram. Find the maximum area that can be enclosed. First step is to define our variables. So we define the width to be X, the length to be Y, and the area, which is the product of the two because it's a rectangular shape. The objective is to maximize the area X times Y. We have 240 feet of fencing. That makes it the limiting factor, the constraint. So the constraint is 240 feet of fencing. 1 and 2 and 3X. 1Y, we don't need anything on this side of the creek. Therefore, 3X plus Y must be 240 feet. Area is a function of two variables, X and Y. So we use the constraint to solve for one of the variables. We're going to solve for Y. And so we are going to replace the y with 240 minus 3x. A becomes a function of x, a of x. So now, again, please understand this means a function of two variables, x and y. Now we can say a is function of one variable, x. And we figure out the domain is 0 to 80 because x represents the dimension, so it has to be positive on the one hand. On the other hand, if we set this one equal to 0, x becomes 80. So when x is 80, the area becomes 0. That can't be. And if you choose a number larger than 80, this 240 minus 3 times x becomes negative. Times positive is negative. The area can't be negative. So that would be the domain, everybody. We distribute, we get 240x minus 3x squared for the sake of the next part, which is differentiation. We want to find the CP, so first we have to find a prime of x, which is 240 minus 6x. Set it equal to 0 to find the CP, and that becomes 40. I can do the first or second derivative test. Second derivative test is easier. I get simply -6. Remember, I'm just interested in the sign, and because it's independent of x, if you plug in any number, makes no difference. So it's negative, which means looks like that, concave down. Concave down means maximum occurs. When x is 40, we go back to the constraint always to find the missing y, 3 times x, which is 40, meaning 120, plus y is 240, and y becomes 120. So the maximum is 40 times 120, which is 4,800 square feet, everybody. Example 4, a box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimension that minimizes the amount of material used. First, a piece of information from algebra geometry. This is a rectangular solid, also known as a prism. The length, the width, the height. If you multiply all of them, you get the volume. Surface area refers to gift wrapping. If I want to gift wrap, that's the concept of a surface area. I hope you see right in front, we have the length times the height, and we have two of them, the one in front and the one in the back. The base is length times the width. We have two of them, the bottom and the top. And the side is the width times the height. We have two of them on the right and on the left. And that's why we have surface area 2 times the sum of those three pieces. If this shape is a cube, meaning the length and the width and the height are identical, We call it a cube. The volume is S cubed. Surface area is 6 times the area of one side, one face, 6S squared. This one has a square base. So let's define our variables. The variables are x times x times h. So those are the dimensions we have to define our variables. I can't emphasize this enough, everybody. And now, what is the objective? Find the dimensions that minimizes the amount of material used. If we were to gift wrap this, we would have this front face there having the area of x times h. And because the base is square, all sides are identical. So we have x times h, and we have 4 sides, 4xh. The base has area of x squared. So the top also the same thing, plus 2x squared on a normal basis. However, it indicates that it's open top. We don't need it for the top. And therefore, the objective is to minimize the surface area, which is 4xh, 4 sides, and 1x squared, not 2, because it's open top. Simply 4xh plus x squared. The constraint is the volume, which is x times h. So the volume is x squared, h equals 32,000. Again, the surface area is a function of two variables, xh, the objective function. So we are going to use the constraint and solve for h. That means divide both sides by x squared. This one, everybody. And now replace the h with that. 4 times 32,000 is 128,000. This cancels out the exponent. We get 128,000 over x plus x squared. Because we want to differentiate this, we're going to bring the x up, and it becomes 128,000 x to the power minus 1 plus x squared. And x is larger than 0 because it represents dimensions, or 0 to infinity. So why is x positive? Because dimensions must be positive. To differentiate, we multiply these two, we get negative 128,000 and x to the power minus 2 plus 2x. Because we want to find the critical points, meaning where the s prime is 0, where it doesn't exist, we are going to rewrite it as follows. We write it in this fashion, negative 128,000 over x squared. And this one, the denominator, the common denominator is x squared. So this is 2x cubed over x squared, or this function. So to find s prime, to find critical point, we set s prime equal to 0. That means the numerator is 0. And also s prime doesn't exist. The denominator equal to 0, that gives us 0, which is not in the domain. But solving this is easy. 2x cubed is 128k, which makes x cubed 64k. And to take a cube root, this becomes x, this becomes 4, and 3 zeros go down to 1. X is 40 centimeters. So we have an open interval with one critical point. So local becomes absolute. But is this going to maximize or minimize? We don't know. We have to check. And how do we check? The easiest way would be the second derivative test. So we are going to differentiate this one again. The product of two negative is positive 256,000 x to the power minus 3 plus 2. So that's s double prime. plug in 40, 256,000 divided by x cubed divided by 40 cubed. Even if you don't know what the answer is, you know this is positive, plus 2 is even more positive. The answer is 6, positive, because we are interested in the sign. Positive means concave up. Concave up looks like that, results in the minimum. So the minimum occurs when x is 40, everybody. Which means what? Which means we have to find the rest of them. And to do so, if x is 40, and we put it here, 40 squared is 1600, divide 32,000 by, and it gives you h equals 20 centimeters, everybody. So let's see what happens when we get that. If x is 40 and h is 20, we write the dimensions as 40 by 40 by 20. So 40 by 40 by 20. What is the minimum material? 4 times x, which is 40, times h, which is 20, plus x, which is 40 squared, resulting is 48, resulting in 4,800 square centimeters. Very straightforward, everybody. We want to find two numbers whose difference is 18 and whose product is a minimum. Again, we start with defining our variables. What are those two numbers? You choose your variable. For example, x and y. Let the numbers be x and y. The objective is to have a minimum product of x times y. And the constraint is the difference is 18, x minus y is 18. And by the way, you may write x minus y or y minus x. The difference will be just the order, okay? You're ultimately looking for two numbers. And you will get that. Now, P has two variables, x and y, so let's solve for y, which means if I put it to the other side, it becomes x minus 18, and put it back into P, and now we call it P of x, because P is a function of two variables here, x and y. By replacing the y, we make it a function of one variable. And it's x squared minus 18x for the next step. Now, the domain is all real numbers. Here's the reason. X can be any number. The reason it can be any number, we are minimizing the product, which means if X is 0, the product is 0, that's fine. If one of the number is negative, that's even better, the product is negative. So that's why there is no restrictions. And so we differentiate this, we get 2x minus 18. To set it equal to 0, we get x equals 9. So the critical point, x equals 9, is this going to maximize or minimize? We have to check. Second derivative test is the fastest and easiest, is equal to 2, because it's independent of x. You don't have to plug in, even if you plug in, makes no difference. All we want is the sign, and it is positive. When it's positive, it makes it concave up. Concave up looks like that, and therefore the minimum occurs when x is 9. If I put the 9 back into the constraint, 9 minus what number is 18 is negative 9. So the two numbers are 9 and negative 9. Now, if instead of x minus y, we had y minus x, then y would be 9, x would be negative 9. It doesn't matter. The two numbers are given. What is the minimum value? 9 times negative 9, which is negative 81, everybody.